Hi everyone, it's Professor Brimington, and today we're going to talk about an introduction to applied optimization. So in the previous section we used derivatives to help us find out what is the absolute maximum and absolute minimum value of a function, and we use it on a closed interval and also on an open interval. However, it's very unlikely that a function will be given to you in a problem to find absolute maximum and absolute minimum problems. In most cases, someone will describe a problem and ask for your help in finding the absolute maximum and the absolute minimum problems. For example, someone may be asking you the following questions. What is the largest volume package which the United States Postal Service will accept? What is the quickest route to arrive at your destination? Or maybe even what is the least expensive way to accomplish some task? In this section, we'll be talking about how to find absolute maximum and absolute minimum values when the function isn't given, and these are called optimization problems. So in this video, we're going to talk about how to solve applied problems that involve optimization of the area and perimeter. In the next video, we'll talk about how to solve applied problems involving revenue, profit, and cost functions. So let's start with an introduction to optimization. The process of finding the absolute maximum or absolute minimum value of a function using calculus is called optimization or applied optimization. The function that we are trying to find the maximum or the minimum value of is called the objective function. And the techniques that we're going to use to solve applied optimization problems are just best understood if we do examples. So let's try example 1. Least cost to construct a rectangular enclosure. The manager of a garden store wants to build a 600 square foot rectangular enclosure on the store's parking lot in order to display some lawn equipment. 3 sides of the enclosure will be built of redwood fencing at a cost of $7 per foot, but the 4th side will be built using cement blocks and they cost $14 per foot. Find the dimensions of the rectangular enclosure that will be the least costly for the store. So with optimization problems, it always helps to figure out what is the function you're trying to maximize or minimize, because that's going to help you set up what is the function and what variables do you need to involve in the problem. Well, we want to find the least cost for this store to actually construct the fence around its property. So we want to find out what is the cost function and then minimize the value of the cost function. So since we're dealing with the rectangular enclosure, let's draw a rectangle first. So we have these 4 sides of the rectangle. 3 sides are going to be formed using redwood fencing, but the last side is going to be constructed using cement blocks. So you have redwood fence on 3 of the sides, and the cement block is going to be just one of the sides. The reason why it's important to separate the redwood fence from the cement blocks is that they are 2 different costs. The redwood fencing was $7 per foot, and the cement blocks were $14 per foot. 2 of the sides are the width, and 2 of the sides are the length of the rectangle. So those are the variables that we need to introduce. Let x be the width of the rectangular enclosure, so that's these 2 sides, and the y will be the length of the rectangular enclosure, and so that will be these 2 sides. Notice that we don't know what x and y are. Those are the unknown variables in the problem because we want to find out what are the dimensions that will give you the least cost to construct this fence around the property. The things that are not changing in the problem are the cost of the materials to build the rectangular enclosure. So the $7 per foot, that's not changing, and the $14 per foot for the cement blocks, that's not changing either. Alright, so now that we know what the variables are, let's talk about the objective function. What is the function that we're trying to maximize or minimize in this problem? So the function that represents the quantity that is to be optimized, maximized or minimized, is called the objective function. The garden store wants to minimize the cost of constructing the rectangular enclosure. So that means we need to find a function that represents the cost of constructing the rectangular enclosure. 3 of the sides were redwood fence, that was $7 per foot, and the remaining side of the rectangle was using cement blocks, which were $14 per foot. So the cost function is this. Capital C for cost function, it's equal to 7x, that is the width using redwood fencing. You also have the other width using redwood fencing, so that's another 7x. You had 1 of the lengths that were using redwood fencing, so that's 7 times y. And then you had 1 length that was using cement block, which was $14 per foot. So that's 14 times y. So the cost will be the cost of each of the sides constructed separately. And so you'll have 7x, that gives you 14x, and 7y and 14y will give you 21y. So now that we have this equation for the objective function, you're going to notice that when we talk about optimization problems, we need some other information in the problem that we can use to either replace the x or the y. When we find the absolute maximum or an absolute minimum of a function, we need only one variable. Right now we have 2 variables, x and y, in this cost function. What other information are we given in the problem that we haven't used yet? We were told that the area of the enclosure is 600 square feet. And so area is length times width. Well, we represented the width was x, and we represented the length as y. So if you have the area of a rectangle, it's length times width, or x times y. X times y is equal to 600 square feet, or feet squared. Well, this is another equation that involves x and y. Let's take this equation and solve it for x. So you'll have x times y equals 600. If you solve for x, then you'll divide both sides of the equation by y. And so x is equal to 600 divided by y. And now you have x isolated on one side of the equation. Now we're going to use the substitution method from algebra. If you take this x equals 600 divided by y and plug it into the cost function, then you won't have x's in your cost function anymore. It'll just be the variable y. So substitute x equals 600 divided by y into the cost function, capital C. And so C is equal to 14 times x plus 21 times y. Take the x and replace it in parentheses with 600 divided by y. So 14 times 600 divided by y plus 21y. And now simplify. 14 times 600 is 8,400, and the y is in the denominator, so 8,400 divided by y plus 21y. This is the function that we want to minimize. We want to minimize the cost, and it only has one variable now, just the y. It may have seemed like we actually have done a lot of work so far, but we haven't actually used calculus at all. We just constructed the function c, which is 8,400 divided by y plus 21y. Now let's use calculus methods to differentiate the equation because we know that we want to find the derivative of the cost function to find its absolute maximum or an absolute minimum value. So take the derivative of c equals 8,400 divided by y plus 21y with respect to y. So y is the variable, so that we can find the critical numbers for this function. So if c is 8,400 divided by y, let's rewrite this so that y is in the numerator. So that's 8,400y to the negative 1 power plus 21y, the other term just stays the same. And now take the derivative using the power rule and the sum rule. So the derivative of the left side is c prime. So the derivative of the right side, use the power rule. So take negative 1 down to the front. So it'll be 8,400 times negative 1, so negative 8,400. Keep the y and now subtract 1 from the power. So you have y to the negative 2 power. And the derivative of 21y is 21. Now, just like we've been doing for a while now, we want to find out what are the critical numbers for this function. Where is the derivative 0 or where is the derivative undefined? So we need to simplify this derivative. C prime is equal to, let's move the y to the negative 2 back down to the denominator. So you have negative 8,400 divided by y squared plus 21. Now let's get a common denominator, which is y squared. So let's take the second term, which does not have a denominator, it's just 1, and multiply it on the numerator and denominator by y squared. So negative 8,400 divided by y squared stays the same. The second term becomes 21y squared divided by y squared after you find a common denominator, and now you can make it one fraction. You have 21y squared, subtract 8,400 in the numerator, and the denominator is just y squared. And again, why is this important? Because now we have a fraction that we can set equal to 0, or where the denominator is equal to 0, to find out where are the critical numbers for this function c. So c prime is undefined, that's where the denominator is 0, so y squared equals 0. If you solve for y, you get y equals 0. Now y represented the length of the rectangle. You can't have the length of the rectangle be 0 feet. So this doesn't give you any critical numbers for the function. However, c prime could equal 0. So where is this derivative 0? It's where the numerator is 0. So 21y squared, subtract 8,400 equals 0, and now solve by factoring. There's a 21 in common with 21y squared and 8,400, so factor it out as a GCF. So 21, and you'll have a y squared from the first term, and you'll have a negative 400 from the second term. And it all equals 0. Now, what's inside the parentheses is a difference of two squares. You have y squared, subtract 20 squared to get 400. So this gives you 21 on the outside, times y minus 20 is one factor, and y plus 20 is the other factor, and it all equals 0. So now you have a product that's equal to 0. One of the factors must be 0. 21 can't be 0. So y minus 20 equals 0 gives you y equals 20. And y plus 20 equals 0 gives you y equals negative 20. Now y equals 20 does make sense because that would be 20 feet for the length of the rectangle. You can't have a negative length, so y equals negative 20 is not a critical number. So now rather than making a sign chart for the first derivative and find out where is the function increasing and decreasing, knows that we only have one critical number. We can use the second derivative test for a local extrema to find out what is the absolute maximum and an absolute minimum. So if you use the second derivative test for a local extrema, find the second derivative. So if c prime was negative 8,400 y to the negative 2 plus 21 before we simplified, use the power rule and the sum rule again. So take the derivative of the first term, the negative 2 will come down, so you have negative 8,400 times negative 2, that'll give you 16,800, and then subtract 1 from the power again, so you'll get y to the negative 3 power, and the derivative of 21 is 0, and so this is really a fraction. This is 16,800 divided by y cubed, so that's your second derivative. When y equals 20, that was our only critical number. If you plug 20 into the second derivative, we want to find out is the graph concave up or is the graph concave down at that critical number? So the second derivative would be 16,800 divided by 20 cubed, which is 2.1, which is a positive number. So at y equals 20, the second derivative is a positive number. That means the original graph, which is the cost function, is concave up. That means that there's an absolute minimum for the cost function, and it occurs when y equals 20 feet. So in other words, the length of the rectangular enclosure needs to be 20 feet long with cement blocks for the cost function to be minimized, so that the store has the least cost in constructing this rectangular enclosure. So since they're asking us to find out the dimensions of the rectangle, it's not just the length they were asking for, they're also asking for the width. So earlier we had this equation x equals 600 divided by y, and this is what the equation was when we plugged into the cost function to eliminate the variable x. Let's use this equation to find out what is the width of the rectangle. So if your length is 20 feet, that means x must be 600 divided by 20, which is 30 feet. So your width of the rectangle must be 30 feet, and that's using redwood fencing. And the length must be 20 feet, which was using cement blocks on one side and redwood fencing on the other side. And so all this work means that we have optimized the value of the cost function so that the store spends the least amount to construct the rectangular enclosure. So now that we've talked about how to solve optimization problems, let's go through a strategy that we can use for any applied optimization problem. Solving applied optimization problems. Number one, always read the problem and determine what information is given in the problem and what is the unknown quantity that is being optimized, which is maximized or minimized in the problem. So in the previous example, we knew that we had the length and the width of the rectangular enclosure that were unknown. So we needed variables for x, the width, and y, the length. And we also knew that we needed to minimize the cost that the store is going to use to construct the rectangular enclosure. So we were trying to optimize the cost function. We were trying to find its minimum value. Number two, draw a picture and label any part that may be important in the problem. So in the previous example, we knew that we were dealing with a rectangular enclosure, so we drew a rectangle, and we represented the width as x, and that was using redwood fencing. And we also knew that we needed y to represent the length, and the length was using cement blocks and also redwood fencing on the other side. Number three, list every relation in the picture and in the problem as an equation or an algebraic expression and identify the unknown variables, identify the constraint function, look for words indicating a largest or smallest value. So what we did in step 3 is that we knew we needed to find out the minimum value for the cost function. Well, we used the construction cost for the redwood fencing and also the cement blocks to help us find out what is the function c. We knew that c was 7x, 7x, 7y, and 14y, and if we added all four sides together for those costs, we came up with the cost function 14x plus 21y. What other information we knew in the problem is that the area of the rectangle was 600 feet squared, so that meant x times y was 600. Number 4, write an equation for an unknown quantity. If you seem to have two or more variables, find the constraint equation. Solve the constraint equation for one variable and substitute into the objective function. So what that's talking about is that we had the cost function representing with two variables. We had 14x plus 21y. That's too many variables to find out the absolute maximum or an absolute minimum for a function. So we needed to use the area function. The area function was the constraint. We were constrained to use only 600 square feet. So x times y was 600. If we took that equation and solved for one of the variables, we solve for x, and you plug in or substitute into the objective function, you plug into the function c, then you can reduce the number of variables down to just one. And that's exactly what we did. We had the cost function only in terms of the y. Number 5, use calculus to find the critical numbers of the objective function. Use the methods used in the previous section to find the absolute maximum and absolute minimum of the objective function. Do not forget to check the endpoints of the domain of the objective function. So step 5 is the only calculus step that we actually use in the optimization problem process. You want to find out what is the derivative of the cost function, which is the objective function. And so we found out the critical numbers. We found out where is the derivative 0 or where is the derivative undefined. And we found out in the last example, we only had one critical number. So that meant it had to be an absolute maximum or an absolute minimum. And then we used the second derivative test to find out what is the concavity at the critical number. And that's how we show that y equals 20 was the absolute minimum for the cost function. And then step 6, use the solution to determine whether you have answered all the questions asked in the optimization problems. Just because we found out y equals 20 in the last example didn't finish the problem. They were asking us to find out the dimensions of the entire rectangle. We needed to find the length and the width. So we had to go back and find out what was the value of x, when y equals 20. So each of these 6 steps are what we're going to use for any optimization problem. So let's try another example. Example 2, maximum area of a rectangular region. A builder has only $840 to spend on a fence to enclose a rectangular area. The fence along 3 sides is to be made of material that costs $6 per foot, and the material of the 4th side costs $18 per foot. Find the dimensions of the rectangular area that produces the maximum area. What are the dimensions of the rectangular area? So this problem may seem similar as the last example. We're still dealing with the rectangle, but we're not talking about the cost being minimized. We're talking about finding the dimensions of the rectangle so the area is maximized. And this time we're not told the area of the rectangle, we're told how much money that we're allowed to spend, $840. So let's start off with the variables that represent the unknown quantities in the problem. We have a rectangle and we don't know what the length and the width of the rectangle are. We need to find out the dimensions of the rectangle. So again, let x represent the width of the rectangular area and let y represent the length of the rectangular area. And also identify what is the function that we want to maximize. We want to maximize the area. So we're going to be trying to find a function that represents this area of the rectangle. And again, notice that $6 per foot and $18 per foot, those are constant. Those do not need variables because it's always $6 per foot for 3 sides to construct those, and it's always $18 to construct the last side, the 4th side. Now the second step. The second step is to draw a picture and label any information given in the problem. So again, we have a rectangle. 3 of the sides are using material that costs $6 per foot. So $6 per foot for one side, the second side, and the third side are all using material $6 per foot. But the 4th side, it costs $18 per foot. So let's just represent this last side. This remaining side is $18 per foot. So now that we have the variables, let's talk about the objective function. What is the function that we want to find out the maximum or the minimum value of? The builder wants to find the dimensions that will give them the maximum area or maximize the area of the rectangular region. The area function or the objective function would be A equals the area of a rectangle is again length times width or x times y now that we have x is representing the width and y is representing the length. And so A equals x times y. Now notice if you want to find the maximum or the minimum of this function, you need only one variable. Well, we have 2. So we need to use information that was given in the problem to help us substitute and so that we can reduce the number of variables down to just 1. So notice that we only have a certain amount of money that we can spend in this problem. We only have $840 for the construction of all 4 sides of this rectangle. 3 of the sides of the rectangle are using materials that are $6 per foot, and the last side is using materials that cost $18 per foot. Let's come up with an equation that represents the cost of the materials. So the cost function would be C equals, it was $6 per the width, $6 per the width, $6 for one of the lengths, and $18 times one of the lengths. So you have 6x, 6x, 6y, and 18y. If you combine all the like terms, you have 12x plus 24y. And we know how much money we have for the cost function. We only have $840 to spend. So 12x plus 24y equals 840. So this equation involves both variables x and y. If you take this equation and solve for either x or y, then we can use it and substitute into the area function to reduce the number of variables down to 1. So if we solve this equation, 12x plus 24y equals 840, let's solve for y. Then you want to get y by itself on one side of the equation. So 12x plus 24y equals 840 is the same thing as 24y equals, move the 12x to the right side of the equation, so negative 12x plus 840, and divide both sides of the equation by 24 to get y by itself. So y is equal to negative 12 divided by 24 is negative 1/2, keep the x, and then 840 divided by 24 gives you 35. And now here's the important step. We have this equation that has y by itself, so take this equation and replace it for this y in the area function, the objective function, because we want to reduce the objective function down to one variable. So substitute y equals negative 1/2 x plus 35 into the area function. So a was equal to x times y. Take the y out and replace it with negative 1/2 x plus 35. And so x times negative 1/2 x plus 35. Use the distributive property to simplify. And so x times negative 1/2 x is negative 1/2 x squared. And x times 35 gives you 35x. So again, it may seem like we actually have accomplished a lot of work. We've actually have done 4 of the 6 steps in the process of solving applied optimization problems. The 5th step is to now use calculus methods to find out what are your critical numbers, so you can find out what is the maximum or the minimum value for this function that represents the area. So now use calculus methods to differentiate the equation because the equation now, the a, only involves one variable. It involves x. So a is equal to negative 1/2 x squared plus 35 with respect to x. So x is the variable so that we can find out the critical numbers. So since a is a polynomial function, it will be very easy to find its derivative. So a is equal to negative 1/2 x squared plus 35x. So if you take the derivative of the left side, you'll get a prime. And then the derivative of the right side, negative 1/2 is the coefficient, so you keep it. And the derivative of x squared is 2x. The derivative of 35x is just 35. And if you simplify, negative 1/2 times 2, that's negative 1. So you have negative 1x plus 35. And so now it's going to be very easy to find out what are the critical numbers. So notice that a prime is undefined, never occurs because you do not have x in the denominator. A prime equals 0 gives you an equation to solve. You have negative x plus 35 equals 0. That means x equals 35 is the only critical number for this function. So now let's use the second derivative test again to find out, is this critical number going to give us an absolute maximum or an absolute minimum for this function? And so if your first derivative is a prime equals negative x plus 35, now take the second derivative. The second derivative would be a double prime. The derivative of negative x is negative 1, and the derivative of 35 is 0. So the second derivative is always negative 1, which means the second derivative is always negative. That means that the area function is concave down for all x values. And so since the area function is concave down, that means that we have an absolute maximum value at the critical number. So the absolute maximum occurs at x equals 35 feet, and that is representing the width of the rectangle. And since we want to find out what are the dimensions of the rectangle that gives us the maximum area, we need to find out the length. So now substitute x equals 35 into the equation that we had earlier in the problem. We had y equals negative 1/2 x plus 35. Let's replace x with the critical number x equals 35 to find out the length. So y is equal to negative 1/2 times 35, then plus 35, and that will give you 17.5 or 17.5 feet. So the maximum area of the rectangle occurs when the length is 17.5 feet and the width must be 35 feet. So this is a good place to stop our video now that we talked about an introduction to optimization problems. If you have any questions about any examples in this video, please let me know. Or if you have any questions while you work on the homework for this section, please let me know that as well. And I'll see you at the next video when we talk about how to maximize profit or minimize costs that arise from economics and business applications.